All right, announcements. We have an assignment due tonight, the recursion assignment. I've seen and heard some questions from people trying to overcomplicate it. This should be the simplest assignment that you've had so far in here. Each of these functions should be between 4 and 10 lines at most. They don't need parameters. You don't need helper functions. Just a few lines will get the job done. So try to think recursively and think about how can I do this in a nice recursive fashion. It's unfortunate that I'm forcing you to do clear recursively because it is so much easier not recursive. Head equals null, tail equals null, done. Unfortunately, there'll be a couple more lines than that. All right, today we're talking about queues. We've finished up talking about stacks, and now we have, every time I look at this word, there's no way you pronounce this queue. It's absolutely wee-wee, and no one can make me think or say it would be spelled otherwise if they meant it to be pronounced queues. But queues are a natural pairing to stacks because they are very similar, but at the same time, they solve a different subset of problems. So we talked about stacks being the life of the party. They're a last in, first out structure. We want to get the same kinds of guarantees that we can get out of a last in, first out structure that we get in a first in, first out structure. So last in, first out is like a stack of plates. The last objects that we place onto the stack is the first item that we go grab from the stack. In a first in, first out structure, the last item that we placed in there is the last item that's going to be taken out. The item that has been in the queue the longest is going to be what is removed when we go to do the stack equivalent of a pop that we don't call a pop for some reason. So rather than thinking of a stack of plates, think about standing in line at a grocery store. Is this last in, first out, or first in, first out? First in, first out. Imagine how fun it would be going to a grocery store if the checkout line was a stack instead of a queue. If you're the unluckiest person who gets there right before a big rush, you're going to be in line until they close. It's a good thing we do it in a queue order and not a stack order, because otherwise life would be really hectic and there would be some significant politics associated with buying groceries. And we probably have a significantly larger violence problem in the country than we already do. So let's start in some groups thinking about the differences between a stack, now that we've actually gone and programmed a stack and seen it work. What about a structure that works similarly, but has a first in, first out structure instead of a last in, first out structure? Think about the differences. A lot of it's going to be similar, but what additional difficulties do we have using a first in, first out structure compared to a last in, first out structure? Think about that for a few minutes and then we'll come back together and talk about it. So we basically want the same functionality. We want to be able to add to a queue. We want to be able to remove from a queue. Yeah. I think it's the same person. What underlying structure makes the most sense to use here? Is it the same as the stack? Does it matter? What difficulties are you going to experience? Yeah, add a array list or a linked list or some other structure. Does some different structure make more sense? Would you want to use an underlying stack as the structure for a queue? If it's not.
So, yeah, very aggressive.
What happened?
We just couldn't figure it out, but until you like, you put in the Discord, like, you actually don't need anything in the parameters.
Yeah,
Yeah, at least that's after that.
makes it a lot easier to just not even consider the access information. It's like you don't need any of this peripheral stuff. Just focus on right here, right now. The person. So what did we think of? What differences exist? What do we need to be thinking about? Gotta remove the front. We have to remove from the front, so we need access to the front. Unlike the stack, where we could just ignore the front and we only worked with the rear, which meant that it made a lot of sense to just interact with the rear, which we can do in constant time, yeah?
Well, the other thing about the queue is like you have to decide whether you want access to listing you just put into the list quicker or not, because once you put it into a queue, you have to wait until it cycles to the front again.
Right. Yeah, we don't actually want access to it. As soon as we add something to the queue, we don't want to think about it until it's in the front of the line. If you think of a cashier, for instance, now maybe they're thinking about how long is the line? Do I need to call another cashier to the front to handle this long line? But imagine that that's not the case. That's not something that you can do in your job. And now you're trying to figure out, who do I service next? You don't care about the rest of the people in the line. They can be invisible for all you care. You just care about who's in the front, make eye contact with them, make them come up, give you their stuff so you can check them out, so you can get through the queue. So we need the ability to access the front so that we can put stuff in. We need the ability to access the rear so we can take stuff out, or the other way around. It doesn't really matter which way you do it. We just make sure we need to have constant time access to both the front and the rear. Is there a structure that makes more sense to use if we need access to both the front and the rear in constant time? Some kind of linked list. As long as we have a tail pointer and a head pointer, then a singly linked list will work just fine for that. But a linked list, yes, has constant time access to the front and the rear. What about an array list? Yes, so if we take something, if we have to deal with the front for any reason, we have to shift everything back to make room for it. Now, there are some tricks we can use for this in order to make this constant time. But it is much more of a pain than just using a linked list. So the entire reason that we introduce linked lists for things is they're going to show up over and over and over in this course. And this is one of them. A linked list queue is easier to implement than an array list queue. So queue is an abstract data type. We're not going to specify what underlying structure we're using for a queue. So we're not going to say that all queues use linked lists, because you could make a linked list queue. You could make an array list queue. You can make some kind of custom queue that uses a custom data structure that you invent. But the idea is we need constant time access to all of its functions, just like the stack. So we can't access the middle at all, so we can't add in the middle. We're going to assume that we're adding at the rear, as we're thinking about lines. We're gonna add at the rear and remove the front. So again, we can't access the middle for any reason, so we can't add or remove from the middle. We can't add in the front of the queue, no one can cut in line. And we can't remove from the middle or the rear. We can't service someone who isn't first in line. So we just can't access any element in the middle, kind of like the stack, where it was a pain to take the plates off to access a plate in the middle of a stack. We can't even talk to the people in the middle of the line. We can't communicate with any object in the middle of the queue. All we can do is access the element in the front and add things to the back. So again, thinking of a grocery store line, when you get in the line, you would get in line at the back, unless you are a terrible person and attempt to cut. When the clerk yells next, the person who has been in the line the longest goes and gets serviced. So we talked about the underlying structure for a queue. Can we do it with an array list? Yes. Can we do it with a linked list? Yes. With an array list, though, the issue is that we have to figure out how to add someone to the list or remove someone from the list, depending on whichever one is happening at the front of the list. And without any further modifications, that's a linear time operation. So how do we restrict the access to the underlying list? Just like we did with the stack, we're going to make a list, a field of the queue object. And then we're going to implement public methods that restrict the access in just the ways that we're defining for a queue. So we can no longer add at an index like you can with a list. If you're going to make a queue object, if you're going to add to it, and again, we're not going to call it add, but if you're going to add to it, then you have to add at the rear, wherever the rear happens to be. That could be the back of the list or the front of the list. So there's a big challenge with queues. With a stack, we know right where the top of the stack is based just off the size of the stack. You query the size, you know right where it is. The front and the rear have to be located at opposite sides of the list. So we need access to the first element and the last element. If we're using an array list, this becomes a problem. Every time we take something out, the front of the queue needs to either shift, or the smart thing is we just change where the front of the queue is. So instead of being at index 0, as soon as we remove something from the list, shift the front of the queue to index 1. And that way we don't need to shift everything over. We just know when we call next, instead of looking at position 0, we're going to look at position 1. So we don't want to move every element up one spot. Every queue operation should be constant, otherwise we could just use a list. If there were no way to do this in constant time, we would just want to use a list, because a list can do all of these things, but some of what it can do is linear in nature. We want to restrict that such that we can solve some problems faster than we can with just a list. So we need to keep track of where the front of the list is and where the rear of the list is. So we're going to have 2 additional fields in a queue if we're using an underlying array list structure that says that's where the front is, that's where the rear is. Unfortunately, we add a bunch of elements and we don't have space in our list anymore. We know that if we want to resize a list, that's not a constant time operation anymore. And it seems really annoying or bad to just start ignoring. Every time that we remove from the queue, we're gonna shift the index up one. We have all of this allocated memory that we're just not using anymore. We can't add to it. And it's allocated for something that we're never going to access again. That seems like a problem. Do people visually, does that make sense? Let me draw it out. So we make some kind of underlying array list object. And we fill it with some components. You know, we have 1, 2, 3, and 4 at index 0, 1, 2, 3, etc. And now we want to add again. We want to add something to this queue. Well, let's start by removing. Let's remove the 1. We service that person. We remove the second person in line. Now it's the original third person in line's turn, but a fifth person shows up. We need to resize this list because it's currently only of size 4 in order to be able to add the fifth person. So it's no longer a constant time operation if we're resizing this list to maybe double its capacity, which is what an array list does when it resizes. But now we have an index 4 where we can add person number 5. The issue is, no matter how many adds and removes we continue to do, we're never using this space or this space ever again. This is just dead memory to us. Can anyone think of a way we could get around that? How could we reutilize this memory? Yeah, we need some way of when this fifth person enters, rather than seeing that this list needs to be resized. We could say, if this is the front of the queue, I'm gonna label this F, and this is the rear of the queue. Then we could say, instead, person number 5 comes in here. And now the rear of the queue shifts to be here. And we know that index 2, index 3, looping around index 0 from the front up to the rear has elements or has people waiting to be serviced in line. So we can use modular arithmetic with regards to the size of the underlying array structure to turn this into, if we really wanted to visualize what this is doing, it's more like a circle where we have indices that are index 0, index 1, index 2, index 3. And now we have this circular structure where we have a front pointer now at 2 that says this is the current front of the line, and this is the current rear of the line. And as you add, you move the rear up, mod the size. As you service people, you move the front up, mod the size. And this allows us to continue to have any number of people in line as long as the total number of people in line is less than or equal to 4, because that's the size of our list. We would still have to go through a resize if we wanted to service more than 4 people at once, if we wanted to have a queue of more than 4 people. But you can decide how large of a queue you want to support initially when you make the initial size of your array structure. So you could make this of size 8 when you allocate it. You could make it of size 16 when you allocate it. You could still possibly resize this structure on an as-needed basis. You would just make a new large circle with now 8 elements. And then from the front to the rear, you would start copying in, starting at index 0. So if this is index 0, 1, 2, 3, 4, 5, 6, and 7, you would start at the front and say, until I get to the rear, copy the elements over. So this would be 3, 4, 5. And now you have a resized array that is exactly like when you resize an array list, except now you've started back at index 0 and just copied over from the old front to the new rear, and then you can get rid of this structure. So it's possible, and now the only expensive thing you're doing is the potential resize. If you don't ever resize, then adding is constant. You just look at the rear and bump it up and add something. When you want to service someone, you bump this front pointer up. Questions on this logic? Does this make sense? Give me some thumbs, maybe. How are we doing with this? So it's a little bit trickier using an underlying array list structure. If we're using a linked list, do we have to worry about this? No, there aren't any index bounds. We don't need to worry about shifting things over or modding it by a size because a linked list doesn't have an inherent size. We can always add to a linked list. We can always remove from a linked list. We can always mess with the next and or previous pointers however we want to. So the linked list implementation doesn't have quite as many underlying concerns, which is why in class, we're going to implement the linked list version, and for homework, you're going to implement the array list version. Just so you get a chance to start thinking about this kind of logic, which does show up in other situations. So it's very useful for you to get practice thinking about how do you implement such a structure. It seems like it might be unnecessary for now, but it's very good practice for the kinds of thinking that you use when you're considering what kinds of structures to use, the pros and cons. Sometimes you can't avoid this kind of logic. Questions before I erase? Okay, so I've probably gone through most of the rest of these slides just off the top of my head. So let's see. Solution here is to use a linked list. The head of the linked list is, sorry, the front of the queue is the tail of the linked list. The rear of the queue is the head of the linked list. You can also do it the other way around. You can make the front the head and the rear the tail. It doesn't really matter. It's just kind of the directionality of the flow of the list. Are we flowing from the head to the tail or from the tail to the head? Doesn't matter. It's a queue structure regardless, as long as you are consistent. So let's talk about the actual underlying fields and methods. So to make this work, we need a field for the underlying list. We need a field for the size, the number of elements that are currently in the queue, just so that we can answer questions related to the size. If you're implementing with an array list, then you need a maximum number of elements that can be in the list. That depends on whether you want to support resizing the list or not. If you don't, then you just have some logic that says if we're trying to add and the size is equal to the maximum number of elements, we need some kind of exception that says the queue is full. We also need, if we're implementing with an array list, we need the index of the first element, because the index of the first element will be shifting as we go. And not mentioned here, we need the index of the last element. So we need a front pointer and a rear pointer that says, here are the bounds of our circular queue. All right, what methods do we need to write? The methods are named differently from the stack methods historically. This was done just for you. This is the payoff of years and years of naming these things differently. It's just to confuse and annoy you personally. So when you want to add to a queue, we call it an end queue rather than a push. With a stack, it's a push. With a queue, it's an end queue, and they do exactly the same thing. If we want to remove from a queue, we call it a dequeue rather than a pop. I personally think it looks and sounds a lot better if you say enqueue and dequeue. significantly more fun. Just like before, we can peek, we can look at the element that's at the front of the cube, and we still call it a peek. Because of course we do. We can then have a size, and it is empty. So let's spend a little while in groups or by yourself, write a Q class with an underlying linked list object. And then we will implement it together so that we can see exactly how we can do this. It's exactly like a stack. All of this implementation has the same underlying logic of what we want to do to a stack, except that now we're working with a queue object and we're working with a linked list instead of an array list. Which might make it just a little bit more challenging, but make sure that you use your underlying, if you're programming this, make sure that you're using your underlying linked list code. So don't reinvent the wheel with a linked list. I can show you exactly what I've set up. It's not much, but I have imported my linked list. Just import linked list.star, which it's going to import all of the linked list code that we've done, and this will allow you to be able to say, like linked list, singly linked list equals new singly linked list, and then you can use that object and you have all of the benefits of the singly linked list structure. Now you can either, since I don't have a doubly linked list here, you can either instantiate a singly linked list or a doubly linked list, or even a circular linked list. This is up to you, depending on what functionality you have that works. Do you think you're going to get any additional benefit from using a doubly linked list over a singly linked list? If you think the answer is yes, use a doubly linked list. If you think the answer is no, I would challenge you to use a singly linked list because it saves memory over a doubly linked list. Unless we are using the power of the previous pointer for each of the nodes, then you should use a singly linked list. I'm going to go back and show this material, but I just wanted to make sure that if you are writing this yourself, that you're importing your linked list code, which means you have access to every linked list method. As you're writing NQ, you can use your linked list add, but remember that everything you need to do must be constant time. And some of your linked list methods are not going to be constant. So the challenge is only use calls in such a way that NQ is constant, DQ is constant. Everything is constant. Let's spend a few minutes and get it done. Feel free to pair program with your neighbors as well. It doesn't necessarily have to be an individual task. Here is all your NQ is. Also written in the constructor. I'm choosing to add at the rear of the list, at the end of the list, and I'm gonna be removing from the front of the list. You could arguably do this the other way, and it would be just fine.
So it wouldn't be wrong if you're adding to the head.
Correct, as long as you're removing from the tail. If you're adding to the head and removing from the head, then you have a stack instead of a cube. Yeah. All right, this will be a DQ. Had to add a little bit of functionality to the list and to the node in order to get that to work. So this should probably be in the same package as the linked list so that I could make this increment head protected rather than public, because we don't want an outside user incrementing the head for no reason. There needs to be a reason for them to want to shift where the head of the list is. But that's exactly what we want to do in this queue. So we want to move head to be head.next, which is exactly what this increment head function does. And then I also added functionality to the node. It doesn't change the underlying data. There's still no way to change a node's data, which is good. We don't want to write a set data. But just getting read access to a node's data is important. So in the singly linked node, I added a getter for the data field. So that's all this function is doing, and it's getting the data out of the node that used to be the head. So I store it off because we're going to increment the head, which is going to get rid of it from the list's perspective, and we need some way to access its data to be able to return it. But if we return it before we increment the head, then the method is over and we don't get the opportunity to increment it. So we have to store it temporarily, then move the head, then return that. And since this temp is it's a variable in the scope of DQ, as soon as DQ ends, then Java's garbage collector comes and frees the memory associated with the node that used to be the head of the list. So we don't need to worry about that. So this should be a DQ. Our NQ adds at the end, our DQ removes from the front of the list. What else do we need to implement? Peak size and is empty. Peak should be easy given DQ. No reason these shouldn't be the same type. So I can cast to a T. This will be an unchecked cast, which can be quite dangerous if you just assume that that's the case. But this is basically saying that there's no guarantee that the front of the list is the same type as the node. You could add a node that is a double to a queue that contains an int. As long as you don't do this, this will not have an issue. If you try to do this, we'll get some lovely exception that crashes your program. All right, so that's peak. Size and is empty are going to be significantly easier. So that should be size and is empty, and I think we basically have our basic queue functionality. There may be some additional quality of life things that we would like to do to this queue, but this will give it the absolute basic functionality of being able to NQ, DQ, peak, check the size, and check whether it is empty. And this will allow us to write driver programs that use this structure for some problem that a queue would be able to solve. Yeah,
Would it be bad practice if we did if we used our getter method and just called it index 0 for peak?
you could do that, yeah. warning here. Yeah, it should be parameterized. You're absolutely right. All right, I'm very happy with this queue. Question?
On the DQ, is the list increment head, is that doing the size bindings?
It is not. I definitely need to decrement the size. Excellent catch. Should probably do that before I return.
Did you write get head and get data methods?
Yeah, I wrote the get head and the increment head. So in the singly linked list, increment head just says head equals head dot next. I think this should probably, instead of being public, be protected, and we should throw this queue inside of the same package, and that way only the structures that use the list directly have access to increment head, and the general public who is using and creating a singly linked list does not. But I'm keeping these in separate packages just for ease of use for everybody here and for me to be able to upload them and the associated modules of the class. So big caveat that this is technically what should be done. This should be protected. And the Q linked list class should be in this same package as the linked list because it uses the linked list. We are defining the functionality of the queue, which means that we should be able to manipulate the underlying list in certain ways that the general public should not. But there's no way to do that unless these classes are in the same package. So I've made increment head public, which means that our dumb user can also call increment head and mess up their own linked list without knowing what they're doing, which is bad practice. I just want to make that very clear. And then temp.getData is in our singly linked node. It's just a getter for the data field. All right. Last thing I really want to talk about is the circular queues. So we basically did this already. You're going to be implementing the concept of a circular queue on your next homework. And I don't know, maybe it's 2 homeworks from now. Maybe I make a bigger assignment that's due closer to the next exam because I want to be able to put stacks and queues on that exam. So this next homework is going to be significantly larger than this one. But I'm assuming that after you take the 8, you'll have a little bit more time and hopefully the stress is a little bit removed from taking the 8 and you can focus on some content that's not on the 8, like the stacks and the queues that we're going to be dealing with here before we take an exam next Friday. I'll end class, I guess, with a couple further announcements. There is one more APE study session today at 2:30 down in 216. For anyone taking the 8, highly recommend. And then I'm going to be getting up this new assignment today so that you can start working on it. And I want a study guide for next Friday's exam up by the end of day Friday, so that you have a week to work with that.
What's gonna be your plan for 300 again as well?
So for 300, we're probably just covering new content. For 212, I may be doing some kind of APE study session or a last minute APE cramming of what don't you understand going into it. I can try to work through some examples on the board or something of the sort. That's probably my plan. Because I don't want to have people focusing on, I have this thing upcoming that I need to be focusing on in an hour.
And then is it here?
Yeah, it's gonna be downstairs in 219, I think. And the TA for this class is the helper for the APE as well. So you can ask him APE related questions as well. All right, that's about it for class. Starting tomorrow, we're gonna go over the next abstract data type. And we're gonna start talking about hashing because hashing is very important when we get to structures that have storage restrictions, we're gonna find we have with that. So we'll see you tomorrow for that.